Today we are going to explain some important topics of electrostatic potential and capacitance, which is the second chapter of NCERT Physics class 12. At first we are going to discuss about electric potential. In earlier classes we have learned about electric potential. Whatever, the definition of electric potential is that it is the amount of work done to bring a unit positive charge from infinity to a point in an electric field. To derive the mathematical expression of electric potential, we consider a charge plus Q placed at point O. So, naturally, it will produce some amount of electric field. Now we are trying to bring a test charge, which is Q0, from infinity to a point P, which is at a distance r from the charge Q. Now we are proceed to find the work done to bring this charge from infinity. We assume a small elementary length dx, which is at a distance x from the charge Q. Now, the work done to bring the charge Q0 through a small elementary distance dx against the direction of force is dw is equal to f vector dot dx vector, which gives f dx cos 180 degree. Here, the angle between f and dx is 180 degree because they are opposite in direction. Therefore, we can write dw is equal to minus m into dx. Now, we know the electrostatic force F is equal to k q naught divided by x square. Therefore, we can write dw is equal to minus k q naught divided by x square into dx. Therefore, total work done to bring the charge from infinity to a point which is at a distance r from the charge Q. Therefore, total work done W is equal to integration of dW is equal to minus integration of infinity to r k q naught dx divided by x square, where the limit of this integration is from infinity to r, because we have to bring the charge q naught from infinity to a point P which is at a distance r from the charge Q. Here k, q naught are constant. Therefore, we can write W is equal to minus k q naught whole integration infinity to r dx by x square. Therefore, W is equal to plus k q naught divided by r. This is the work done to bring this test charge q naught from infinity to this point P. So, for unit positive charge, this work done is W by Q naught. This is simply a unitary method. Therefore, electric potential at point P, V is equal to W by Q naught. If we proceed further, then from equation 1, after putting the value of W, V is equal to k q naught by r whole divided by Q naught, which gives kq by r. Here, k is equal to 1 by 4 pi epsilon naught, which is equal to 9 into 10 to the power 9 Newton meter square Coulomb to the power minus 2. Therefore, this is the expression of electric field due to a point charge. Therefore, the expression of potential due to a point charge is V is equal to 1 by 4 pi epsilon naught Q by r. Now, we are going to derive the expression of electric potential on the axis of a dipole. At first, we consider a dipole of length 2a, which is as shown in the figure. We have to find the electric potential at point P, which is at a distance x from the center of the dipole, and the point P lies on the axis of this dipole. Now, the potential at point P due to the charge minus q is v minus q is equal to minus kq divided by a plus x, where a plus x is the distance between the charge minus q and the point of observation P. Here the negative sign is used because for a isolated negative charge, the electric potential is always negative. Similarly, potential at point P due to the charge plus q is V plus q is equal to kq divided by x minus a, where x minus a is the distance between plus q charge and the point of observation P. So, the total potential at point P due to this dipole is simply the algebraic sum of V minus q and V plus q, because potential is a scalar quantity. Therefore, total potential V is equal to V minus q plus V plus q. After putting the values of V minus q and V plus q, we get the expression of potential V is equal to k into P divided by x square minus s square, where P is the dipole moment of this dipole and the dipole moment P is equal to q into 2a. If the length of the dipole, that is 2a, very less than that of x, then a can be neglected. Therefore, from the above equation, we can write V is equal to k into P by x square. Here, k is equal to 1 by 4 pi epsilon naught. And the value of k is equal to 9 into 10 to the power 9 Newton meter square Coulomb to the power minus 2. This is the expression of electric potential on the axis of a dipole. Now, we are going to derive the expression of electric potential at an equatorial point of a dipole. Suppose we have an electric dipole of length 2a. We have to find electric potential at point P, which is a point on its equatorial plane. Now, let the distance of the point P from the center of this dipole is equal to r. Therefore, the distance of the point P from the charge minus q as well as from the charge plus q can be determined by using Pythagoras theorem, which is root over of s square plus r square. Therefore, electric potential at point P due to the charge minus q is V minus q is equal to k into minus q divided by root over of s square plus r square. Here, the negative sign is used because the electric potential near an isolated negative charge is always negative. Similarly, the potential at point P due to the charge plus q is V plus q is equal to k into plus q whole divided by root over of s square plus r square, which is equation number 2. Here, we can get the total potential at point P by simply adding V minus q and V plus q. Therefore, V is equal to V minus q plus V plus q. After putting the values of V minus q and V plus q, we get the total potential at point P is equal to 0. Therefore, electric potential at an equatorial point of a dipole is 0. Now, we are going to derive the expression of electric potential at any general point which is at a distance r from the center of the dipole. We consider a dipole of length 2a. We have to find the electric potential at point P, which is a general point and which is at a distance r from the center of this dipole. If we join a line between the point P and the center of the dipole, then the line makes an angle theta with the dipole moment. The distance of the point P from minus q and plus q charge are small r1 and small r2 respectively. We will derive this equation into different ways. Now, the first method. Here, we consider that the length of the dipole is very much less than the length of the line joining the point P and the center of the dipole. We know that the direction of dipole moment is from negative charge to positive charge. Therefore, it has two components. One is along the line joining and another is perpendicular to the line joining. Therefore, the component of dipole moment along the line joining is p cos theta and perpendicular to the line joining is p sin theta. In the previous expression, we see that the electric potential at an equatorial plane or at a point on the perpendicular bisector of a dipole is 0. Therefore, for the component P sin theta, the electric potential at point P is 0. Therefore, we can get the potential is only for the component P cos theta. We know the potential at any point on the axis of a dipole is 1 by 4 pi epsilon naught P by r square, where P is the dipole moment of this dipole. See, here the component of dipole moment along the line joining the point P and the center of the dipole is P cos theta. Therefore, we get the potential V is equal to 1 by 4 pi epsilon naught P cos theta divided by r square. Now, the above equation can be represented as scalar product or dot product. Therefore, potential V is equal to 1 by 4 pi epsilon naught P vector dot r cap divided by r square, where r cap is the unit vector along the line joining the center of the dipole and the point P. Again, we know the unit vector r cap is equal to r vector by magnitude of r vector, which gives r vector by r. Therefore, the above equation can be represented as V is equal to 1 by 4 pi epsilon naught P vector dot r vector divided by r cube. This is the expression of electric potential at any general point due to a dipole. Now, we are going to derive the expression of electric potential at any general point due to a dipole in another way. Since the distance of the point P from minus q and plus q charge are small r1 and small r2 respectively, so the electric potential at point P due to minus q charge is V minus q is equal to 1 by 4 pi epsilon naught minus q by r1, where r1 is the distance between the charge minus q and the point P. Similarly, the potential at point P due to plus q charge is V plus q is equal to 1 by 4 pi epsilon naught plus q by r2, where r2 is the distance between the charge plus q and the point P. Therefore, total potential at point P is V is equal to V plus q plus V minus q. After putting the values of V plus q and V minus q, we have V is equal to q by 4 pi epsilon naught into r1 minus r2 whole divided by r1 r2. If the point P is at a very large distance from the center of the dipole as compared to the length of the dipole, then we can write r1 minus r2, which we denoted by AD, is nearly equal to 2a cos theta. Since the point P is at a very large distance, so we can write r1 nearly equal to r2. So in case of multiplication, we can take r1 is equal to r2 is equal to r, say. Therefore, the expression of potential can be written as 1 by 4 pi epsilon naught q into 2a cos theta divided by r square. Therefore, potential V is equal to 1 by 4 pi epsilon naught P cos theta by r square, where P is the dipole moment of the dipole, which is equal to q into 2a. We can represent the above equation in terms of scalar product. We know A vector dot V vector is equal to AV cos theta. Therefore, the potential V is equal to 1 by 4 pi epsilon naught P vector dot r cap divided by r square, where r cap is the unit vector along the line joining between the center of the dipole and the point P. Again, we know unit vector r cap is equal to r vector divided by magnitude of r vector, which gives r vector divided by r. Therefore, from the above equation, we can write V is equal to 1 by 4 pi epsilon naught P vector dot r vector divided by r cube. Now, we are going to derive the relation between electric potential and electric field due to a point charge. Consider a charge plus q is placed at origin. Suppose 2 points A and B are separated by a distance dr is on the x-axis, and let the potential difference between the points is dV. Now the work done to move a test charge Q0 from the point A to point B is minus F into dr. Here the negative sign is used in this above equation because the direction of electric field or force is opposite to the direction of displacement. We know that electrostatic force F is equal to Q0 into E, where E is the electric field. Therefore, dW is equal to minus Q0 into E into dr. Also, we know that the work done in moving a test charge from A to B is charge into the potential difference between the points A and B. Therefore, we can write dW is equal to Q0 into dV, because the potential difference between A and B is dV. Therefore, from the equation 1 and 2, we can write minus Q0 E into dr is equal to Q0 into dV. So, we can write E is equal to minus dV dr, which is the relation between electric field and electric potential.